Section 3.6 in our textbooks is titled Proof Theorems About Perpendicular Lines. And we've got all kinds of theorems here, 5 of them total, that we're going to talk through. Most of them are kind of common sense. They should hopefully all make sense. I do want to make sure we talk through them. And then there's just one example we're going to look at today. So generally relatively shorter section here. Up to you if you want to write these down or refer to them in your textbook. They are all in your book. You don't need to know the names of these. Theorem 3.8. So this is just saying it's the 8th theorem in chapter 3 here. Says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. And it gives us a little figure over there. And it shows that angles 1 and 2 do intersect to form a linear pair. And this is saying that angle 1 is congruent to angle 2. Then lines G and H have to be perpendicular to one another. Again, kind of makes sense here. If we have a linear pair, we know that the entire thing is 180. So this angle right here has to be 180 degrees because we have a linear pair. And if angles 1 and 2 are congruent, we can call them both x. And pretty clearly, I add them up to get 180. So each angle is 90 degrees. If I have angles that form a 90-degree angle, that is the definition of perpendicular lines. The next theorem says if two lines are perpendicular, then they intersect to form 4 right angles. So if the lines are perpendicular, each of those angles, angles 1, 2, 3, and 4, all have to be right angles. As always, if I'm going too fast and you're trying to write it down, pause the video, get caught up. Our next theorem, Theorem 3.10, says if two sides of two adjacent acute angles are perpendicular, and the angles are complementary. So if two sides, this side here and this side here, those are two sides of two adjacent acute angles. So angles 1 and 2 are adjacent. They share a ray. We have this whole thing is perpendicular. The two sides are perpendicular to one another. Then by definition, angles 1 and 2 have to add up to 90 degrees. Therefore, they are complementary. So using this figure here, if ray BA and ray BC are perpendicular to one another, then angles 1 and 2 have to be complementary. They need to add up to 90 degrees. And then the last two, and probably the most important two, this one actually has a name other than Theorem 3.11, the perpendicular transversal theorem. Perpendicular transversal theorem. It's saying if lines H and K, line H and line K, if those are parallel, and we have a line, and we know that line, that transversal, is perpendicular to one of the lines, then it has to be perpendicular to the other line as well. So again, we're given that we have two parallel lines. We've got a transversal that cuts through it. This says if that line is perpendicular to one of the lines, well, it makes sense. If these lines are parallel, we know that our corresponding angles are congruent. So this angle, angle 1, and this angle right here, angle 2, have to be congruent. So this is going to be perpendicular to this line as well. If a transversal is perpendicular to one of two parallel lines, then it has to be perpendicular to the other one as well. In Theorem 312, lines perpendicular to a transversal theorem says in a plane, if two lines are perpendicular to the same line, then those lines have to be parallel to each other. And again, that's if this and this, those are corresponding angles. If those are congruent, we know that lines M and N have to be parallel, whether they're perpendicular or not. And then our one example that we're going to work through is a review of several things we've talked about. It asks us to find the distance between the two parallel sides of the figure. We're looking for the distance between the two parallel sides of the figure. So we know if we have parallel lines, the distance between them is always going to be measured by the line that's perpendicular to both. That's the distance between parallel lines. So I think pretty clearly that these lines are not parallel. These appear as though they are. We should probably verify that though. Let's check the slope of this line. I'm going to call that line, let's call it M. Line M has a slope of up 1, 2, 3 over 1, 2, 3, 4. So line M, the slope is 3 over 4, I think I said. This line down here doesn't pass through a point exactly here. Let's use that point right there. This one here, we're going to call this line N. Up 1, 2, 3 over 1, 2, 3, 4. Yeah, so the slopes are the same. So because they have the same slope, we know that lines M and N are parallel. To get the distance between them, we need the perpendicular line. Well, this side over here appears as though it might be perpendicular. Let's call this line L. And let's check to see if that is a perpendicular line. We're going down 1, 2, 3, 4 over 1, 2, 3. Notice our slope is indeed the opposite reciprocal of both lines M and N. So this line is perpendicular here. So if I can find the distance of this line, the length of that segment, then we know the distance between the parallel sides. To find the distance, I know the endpoints. This endpoint is at what, 4, 5? And this endpoint is at 7, 2. And it's been a minute, but we do know how to find the distance between 2 points. Distance between 2 points, we use the distance formula. Distance between 2 points is equal to the square root of x sub 1 minus x sub 2 squared plus y sub 1 minus y sub 2 squared. And we have our points, 7, 2, and 4, 5, so we can plug stuff in here. So I'm going to use this as 0.1. So 7 minus 4 squared and 2 minus 5. 3 squared, 3 squared, negative 3 squared, root 18. Should probably reduce it. Factor of 18. That is a perfect square. 9 times 2. And the distance between them is 3 root 2. 3 root 2. You could get an approximation of that. We know it's between square root of 16 and square root of 25. So between 4 and 5. And I didn't read my graph very well here. This line, this point right here, probably should have counted instead of relying on these numbers that are right between here. This is 1, 2, 3, 4, 5. That's at 6, not 5. Tag on. Anyway, that changes this to 6. Negative 4 squared, that's 16. 9 and 16 make 25. Square root of 25 comes out nice and easy, and we don't even need to reduce. Should be 5. Sorry about that. But if you had gotten root 18, we know how to reduce that to 3 root 2. That is it for today's notes. Reach out if you're having any questions.